Hello, everyone. This is a platform for the pure mathematics courses, and we are going to start a new course on the complex analysis, a course where algebra and geometry meet to reveal the deep structure of the complex plane. Over this series, we'll explore everything from the foundation of complex numbers to powerful theorems like Cauchy's integral theorem, all while highlighting their applications in physics and engineering. By the end of the course, you will not only compute complex integrals, but you will understand why they work. So, um, moving forward, here are the is a brief outline of course contents and modules. This is the list of things that you will learn in this course. Basic introduction to the algebra of complex numbers, geometric representation, functions of complex variables, Cauchy-Riemann equations, elementary functions, um, different type of theorems, complex integrals, series, Taylor's and Lorentz series, singularities, and the theorems related to singular points, and then the Mobius transforms and conformal mappings. By the end of this course, the student should be able to represent complex numbers algebraically and geometrically, define and analyze limits and continuity for complex functions as well as consequences of continuity, apply the concepts of analyticity and Cauchy-Riemann equations, and check why these results are so powerful, analyze sequences and series of analytic functions, and seek the types of convergence, evaluate complex contour integrals and see how powerful they are in solving the complex integral problems, Cauchy integral theorems and its various variants, and representing functions as Taylor's and Lorentz series, how to represent a different type of function in form of series, classify singularities and poles, find residues, and using residue theorem, evaluate complex integrals. These are the recommended books uh, uh, that you can take help from, and we'll start with the journey of complex analysis. Follow for the upcoming lecture series. Thank you.